This is the presentation of our paper Preventing Unconstrained CBF Safety Filters Caused by Invalid Relative Degree Assumptions. My name is Lukas Brunke, and this is joint work with my colleague Siqi Zhou and my supervisor, Professor Angela Schoellig. The goal of our work is to design a safety filter that can be applied to real-world robotic systems. We consider continuous time control affine systems, and the goal is to keep the system inside a safe set C. First, some important background on control invariance. Intuitively, starting in a set C with state x at time t is equal to 0, if there exists a feasible control input that keeps the system inside the set for all future time, the set is called control invariant. We refer to this as safety. In this work, we express safety through control barrier functions, or CBFs in short. A CBF is a continuously differentiable function, and its zero superlevel set is the safe set. The boundary is given by the states where the CBF is 0. The CBF condition in equation 1 bounds the Lie derivative, or time derivative of the CBF, with respect to the system dynamics. This bound uses a class kappa function, as shown in the bottom right. These functions pass through the origin and are strictly increasing. Let's look at the CBF condition in more detail. The CBF condition is a scalar condition for control invariance. So what does this mean? On the boundary, this means to return back into the safe set. And inside the safe set, you're almost free to do whatever you want, but you're not allowed to approach the boundary too quickly. CBFs are typically used in safety filters. A safety filter takes in an uncertified control input, verifies and potentially modifies the input, such that a certified and safe control input is applied to the robotic system. The CBF safety filter is implemented using a quadratic program. The objective is to match the uncertified control input as closely as possible while satisfying the CBF condition for safety. We implemented the CBF safety filter on a quadrotor. The goal here is to track an unsafe reference in magenta, as the safe set, here the boundary in blue, is violated. The goal of the safety filter is to prevent the quadrotor to leave the safe set. You can see that there are oscillations in the closed loop trajectory and that the safe set is actually violated. So why is this happening? The first problem is caused by the relative degree of the system. The CBF definition assumes relative degree of 1 over the entire system. It turns out that this assumption is often violated in many examples. Intuitively, the relative degree indicates the number of times the CBF has to be differentiated along the dynamics until the control input appears. If the relative degree is not equal to 1, then the CBF optimization reduces to an unconstrained optimization problem, such that the potentially unsafe control input can be certified. Let's take a look at an example with linear system dynamics. If the system dynamics are LTI and the CBF is linear, and the constant Lie derivative is non-zero, then the relative degree is equal to 1 everywhere. Also see the figure on the right. Therefore, the safety filter is always constrained, and the conditions for applying a CBF are met. Let's consider another example, again with linear system dynamics and a linear CBF. Now, in the case that the Lie derivative is 0, then a higher order CBF can be used to still achieve safe operation. You can also see this on the right, but now using the first order CBF in the safety filter leads to an unconstrained safety filter as the Lie derivative with respect to the input dynamics is 0. Therefore, a higher order CBF formulation has to be used in this case. Let's consider a third example, where we have a linear system now with a quadratic CBF. In this case, the relative degree is state-dependent, and there's a line of states where the relative degree is not equal to 1. For those states, the control input has no effect on the condition, and arbitrary inputs can be certified, such that the safety filter is unconstrained. The second issue is that we cannot determine new control inputs infinitely fast and only get discrete measurements from the system. This means whenever the relative degree is not equal to 1, we apply arbitrary control inputs for the duration of the sampling time. So how can we avoid this? First, let's recap the standard CBF formulation. In the standard CBF formulation, we only have one CBF constraint. However, for certain CBF candidates, there are states where the Lie derivative may become 0. And in these states, the safety filter becomes unconstrained. There's no bound on the control input that can be applied to the system. To avoid this issue that's caused by the relative degree and the discretization, we propose to use multiple CBFs. The idea is to design the CBFs in a way such that at least one CBF has a non-zero Lie derivative such that the safety filter is constrained. In the depicted setup on the left, anywhere inside the safe set, a one-dimensional control input is always guaranteed to stay inside a compact interval. We demonstrate the effectiveness of the multi-CBF safety filter on the same quadrotor example from the beginning. Now we are able to prevent oscillations in the closed-loop trajectory, and the system stays inside the safe set. For more details on our work, including the theory and proofs behind this method, please refer to our paper listed in the description. Thank you very much for your interest.